So now we are going to derive the solution for the transient for the Couette flow. So remember, a Couette flow is a flow in a gap. We have a 2D planar flow, and the gap width we're going to call d. And what's going to happen is at the beginning the flow is 0, is at rest, and at t equals 0 we're going to start moving the top plate. And we'll move it at a velocity capital U, and we only do this at time t. So for times t is larger than 0, the top plate velocity is equal to U. So the flow is unsteady, so we don't neglect the partial U partial t term. And what are the equations which are governing this problem? What do we have to solve? Well, first, oh sorry, I forgot to say. And for a Couette flow, there is no pressure gradient across the channel here. So we have the same pressure at the inlet than we have at the outlet, and because the pressure gradient is continuous, it has to be equal to 0 everywhere. So the flow is really driven by the motion of the top plate. Now, what are the equations that we need to solve? First of all, we need to solve the x momentum equation. So that is simply partial u partial t is equal to the kinematic viscosity times the second partial of u with respect to y. Then we need to impose the right boundary conditions. And what are our boundary conditions? Our boundary conditions are simply the no-slip boundary condition on the bottom plate at y equals 0, and on the top plate at y equals d. And at the bottom plate, our no-slip boundary condition just means that the velocity has to be equal to 0 because the plate is not moving. And on the top plate, and that is only true for times larger than 0, we have that the top plate velocity is equal to capital U. And then there's a final condition that we have to impose because we are looking at an unsteady case, and that is the initial condition. What is the flow field at t equals 0? And we just said at t equals 0, we're assuming the flow to be at rest. So we could solve for the velocity field u, but usually what you do is you actually solve for the transient. So if you're thinking about the velocity field u, you can write the velocity field u as so the velocity u, you can think of the sum of a transient, which depends on the position y and on time, plus a steady state, which is only a function of y. Now this here is our steady state. Our steady state we computed before, right? So the steady state solution is just the steady state Poiseuille profile, the constant shear, so u is equals to capital Uy divided by d. And the difference between the real velocity, the velocity field, the unsteady velocity field, and the steady state is what is called the transient solution. And so as you see, when time goes to infinity, when time goes to infinity, this velocity field here, our unsteady velocity field, is going to become more and more like the steady state. It's going to converge to the steady state, right? And the reason why usually we solve for the transient and not the steady state is because the transient goes to 0, right? So if you think about at the initial time, your transient is non-zero transient solution, because this is equal to 0. Your transient is going to be equal to minus the steady state, and then the transient is going to go to 0, and eventually your solution is going to become the steady state. So this is standard in applied math. Usually it's easier to solve for the transient instead of solving for the velocity. So that's what we're going to do. And so we're going to reformulate the problem really quickly just in terms of the transient. So we're going to rewrite the x momentum equation, the boundary condition, and the initial condition for the problem. The same problem, but instead of writing the problem for u, we'll write it for the transient. So here are our governing equations for the transient solution. We'll write our transient in terms of our solution u, for which we've already formulated the problem, minus the steady state, which we know, which is actually not a function of time. So let's see what happens to the governing equations. So this is the x momentum equation. When we write the governing equation for the velocity, right? Of course, the steady state already satisfies the momentum equation because the steady state is not a function of time, and that the second partial of our steady state with respect to y is equal to 0. And therefore, our governing equation for the transient, not surprisingly, is the same governing equation as the governing equation for for the solution, for the total solution. So partial ut partial t is equal to the kinematic viscosity times the second partial with respect to y of the transient. Okay, let's look now at the boundary conditions. Right, so our boundary conditions at the top plate, right, u, we said that this velocity has to be equal to u. This is equal to the transient's velocity plus the steady state velocity, but the steady state velocity we know is equal to u. Right, our steady state velocity on the top plate is equal to u, and this here has to be equal to u, and therefore you see that the transient condition for the transient's velocity at the top plate has to be equal to 0. Right, this u cancel, and this has to be equal to 0. What is the boundary condition on the lower plate? Well, the boundary condition on the lower plate is the same. We write that the sum of the velocity of the transient at the lower plate plus the steady state has to satisfy the no slip, which is equal to 0, but our steady state velocity at the bottom plate is equal to 0, and therefore we see that our transient has actually homogeneous boundary condition. This is why also you saw for the transient here, because the transient has homogeneous boundary condition. That means that the boundary condition both at 0 and d are equal to 0. That's important. Okay, the final thing we have to see is the initial condition, and that we've discussed before, right? So if you're thinking about your initial condition, what is the flow velocity field at t equals 0? At t equals 0, we know that our total flow velocity field has to be equal to 0, right? Because initially the flow is at rest. And we know that our steady state is uy divided by d, and therefore you directly see that your transient, if you're solving for the transient, then the initial condition for your transient is going to be minus u times y divided by d. So this is here our initial condition for the transient. So what we need to do now is solve this problem, this PDE. Right, it's a partial differential equation subject to those boundary condition and this initial condition here. Okay, so how do we solve for the transient? So let's start with the governing equation. So this is the z momentum equation. So we saw that our momentum equation we're solving for u is partial u partial t equals to mu second partial of u with respect to y. This is the heat equation, and a transient satisfies the same equation. Now, this equation is a linear equation, and so when you have a linear equation, PDE, one typical thing that applied mathematicians would do is what they would call try to find a solution using the separation of the variable. So that is trying to find a solution. You see that in your PDE you have time derivatives and you have derivatives with respect to y, and so the idea is to try to find a solution under the form of the product between a function of only time and a function of space only. So there is no guarantee that we can find a solution, but if when the equation is linear, actually, that's the first thing you would do, and usually it works, right? So this is what is called an ansatz. Right? We haven't solved for anything, but we're just saying at this point, let's see if we can find a solution for the transient, which we can write as the product between the function of only time and a function of only y. So if you plug in this ansatz into your governing equation for the transient, then you get that partial with respect to t of this ansatz is just the time derivative of f times g, and that this has to be equal to the kinematic viscosity times, when you take the second partial of this function with respect to y, this gives you just f of t times the second derivative of g with respect to y. Now what we can do is to rewrite this equation and put all of the function which depend on t on one side and all of the function which depends on y on the other side. And so that gives us the following. So then we have 1 divided by nu times f prime divided by f is equal to g double prime y divided by g of y. And what is interesting here is that if you think about your two terms, on the left-hand side, you have a function which is a function of time only. There is no dependency on the space derivative y, on the spatial, not derivative, on the spatial coordinate y. And on the other hand, here you have a function which is a function of y only, right? And so the only way that a function of time can be always equal to a function of space, of the space derivative, space variable, given that t and y are entirely independent variable, is if these two functions, these two sides, are equal to a constant. Because otherwise you cannot have the two be equal to 0. So you see that from our ansatz solution we find that this should be equal to a constant, and we're going to call this constant minus omega squared. All right, so now we can solve for these for this PDE by simply writing by solving two ODEs. So the first one is comes from this here. So if you're writing that f prime divided by f times nu is equal to minus omega squared, then this becomes the ODE f prime is equal to minus mu times omega squared times f, which is here a first order linear ODE, and you know that the solution to that, or you should know, these things you have to know. If you don't remember these, you have to go back to your undergraduate differential calculus. The solution to that is a decaying exponential, right? And so the solution is, in general, an exponential to the minus omega squared times t. And that is, of course, good news, because remember we said the transient has to go to 0. And so here we find that the time dependency that we find indeed is a function that goes to 0. And note that this here will give you a time scale. One thing which I haven't noticed, which I haven't mentioned, is that of course this omega here at this point is completely unknown, right? We had just said this has to be a constant, but we don't know much about this constant, right? And I took it negative on purpose, because if you don't take a negative constant, then this goes to infinity, and that can't be. Right, so I already knew, I put the negative sign here because I already knew that if I hadn't put a plus, if I hadn't put a negative sign here, at this point I would have deduced that this needs to be a negative constant, because otherwise my transient will never go to 0. It will actually blow up, which makes no physical sense. Okay, so indeed this here, it's important to note that it is consistent with a transient, so it goes to 0. Now we solve the second ODE. Right, this is g double prime plus omega squared g equals to 0. Remember, this comes simply from the fact that g double prime of y divided by g prime is equal to minus omega squared. And a solution to that is a combination of cosines and sines. Right, this is the solution to a second order linear ODE. Our solution here is written as the sum of a cosine of omega y plus a sine of omega y. And so now we have the form of our solution, and we need to satisfy, this is our governing equation, that was I. Now we need to satisfy our boundary condition. So what are our boundary conditions for the transient? Remember, we have homogeneous boundary conditions, so the velocity both at y equals 0 and at y equals d has to be equal to 0. Let's start with the velocity condition at y equals 0. So we have at y equals 0, this will be equal to, so I forgot to put the f of t, but it doesn't matter. You see that this is going to be equal to 1, right? This exponential here. So I have g1 cosine omega 0 plus g2 cosine omega 0. This is equal to sine omega 0 is equal to 0, so it's just equal to g1, and therefore that gives us that g1 has to be equal to 0. Let's look at the boundary condition at y equals d. At y equals d, we have that g1, g2, so g1 is equal to 0, so g2 sine omega d has to be equal to 0. And you see that in general this is not true. The sine function of omega d is not going to be equal to 0, except if omega d has particular values. And so if omega d is equal to 0, pi, 2 pi, 3 pi, you know that the sign of these numbers is going to be equal to 0. And therefore, that imposes a condition on omega d, and we get that omega d has to be equal to a multiple of pi. And therefore, that imposes that omega has to be equal to k pi divided by d for k equals 0, 1, 2, 3, and so on. So you have many solutions, and all of these solutions you can write as the following, right? You can write as your omega function, your g function, so sine of k pi y divided by d, so this part here, the g, this is g, times f here, times exponential minus mu. I'm replacing the omega by the value that it should have, k pi divided by d, so k pi squared divided by d squared times t. So all of these for any value of k is a solution which satisfies our governing equations and satisfies also our boundary conditions. Okay, so now we found a or many for any value of k. These are solutions. So we found many solutions of our governing equations and our boundary condition for the transient. But what we haven't satisfied is the initial condition. So we need to satisfy the initial condition for our transient. And remember, the initial condition is the fact that the transient is equal at time equals 0 to minus the steady state. And you can see here that there is no way we're going to have this satisfied here, because those functions, if you put t equals 0, this is equal to 1, you just have ck times a sine, and this sine is not our steady state. Our steady state was our linear shear profile. But what you can do is the following, right? So to satisfy the initial condition, we can write the transient ut as, and because the equation is linear, we can write it as a superposition of the solution that we found, right? We can always, because these are solutions, we know that if I'm adding two of these solutions, I still have a solution because my boundary conditions are homogeneous and because my ODE is linear. And therefore, I can write this as a superposition of these for any, this is because of the linearity, and that is for any value of k, right? For all the different values of k, I can take all values of k, add all of these terms, and I still have a solution. And so now what we need to find are the ck coefficients that make sure that this superposition satisfies my initial condition. Right? So I need to write that ut, my transient, is going to be equal to these. It's going to be equal to these solutions here. Right? So I'm going to write ut is equal to ck times my function f times my function g. But I'm not just taking one of these, I'm taking the sum of all of these for an infinite series of k, right? And then you see directly what those ck's are going to be. Those ck's are going to be the Fourier coefficients of the decomposition, of the Fourier decomposition of minus the steady state. And so to find the ck, we're going to look for the ck such that this our transient at t equals 0, right? When time here is equal to 0, this is equal to 1. So at time equals 0, our transient is just equal to the sum of the ck times sine k pi divided by d y. You see that this is a Fourier series decomposition is equal to minus us, to minus our steady state. And remember, our steady state is just here, it's just minus uy divided by d. So this is how you find a solution to your unsteady, to the transient of your Couette flow.